Good afternoon, everyone. My name is Anjas Prastya Hutama, and I represent my team to present our project about production and characterization of nickel-rich NCA cathode material for high-capacity NCA graphite secondary battery fabrication. Based on the type of lithium-ion battery, including lithium metal chalcogenides, which is the first generation of rechargeable lithium-based batteries and is a development of reversible lithium mobility concept. Then lithium metal oxide, which is the first commercialized lithium-ion battery, has high energy and power density batteries and high voltage batteries, but has disadvantage of expensive raw material. And the lithium metal phosphate, which has the advantage of cheaper and safer lithium-ion batteries and long life cycle, but has the advantage of low energy and power density. Lithium-ion battery technology for EV require a battery that has a high voltage and large capacity. Therefore, EV technology use metal oxide-based batteries. Metal oxide batteries contain a lot of cobalt and it's very harmful to the environment. Research has conducted how to reduce cobalt but not reduce performance by replacing it with nickel. NCA is a material that is classified as nickel-rich. Lithium nickel cobalt aluminum oxide, or NCA, is considered one of the most promising cathode material for lithium-ion batteries, owing to its excellent properties such as high Coulombic capacity, energy, and power density. Currently, NCA with high nickel content preferable because nickel is less toxic and as costly as cobalt. In addition, the nickel-rich cathode material has a higher capacity than high cobalt LCO. Several methods that can be used to synthesize NCA materials include solid-state reaction, spray pyrolysis, flame spray pyrolysis, salt gel, molten salt reaction, which have drawback including decomposable raw material at certain temperature range, expensive raw material, nitrogen and sulfate pollution. Oxalate precipitation method is the most effective method because it has advantages including 3-in-1 roll, single step, fast reaction and short retention time, loose particle and ease of separation, less pH dependent, and less ammonia consumption when compared to using carbonate and hydroxide, which have many disadvantages as above. The NCA precursor were synthesized by co-precipitation method using oxalate and then heated 2 times at high temperature, and the NCA material was analyzed using SRD, FTR, and SEM. NCA material had then assembled into battery and tested for battery performance. Result and discussion. To assure the formation of the oxalate precipitate of NCA, the dried precipitate was analyzed using SRD, FTR, and SEM. The SRD peaks can be attributed to nickel oxalate dehydrate compound provided in the figure. The peaks observed are highly crystalline, indicated by the sharp peaks on the battery. Infrared absorption pattern also confirm the presence of oxalate. The as prepared in NCA oxalate powder are loose, quasi-cubical shape with smooth surface. The edge of the particle as well as the grains can be clearly observed. The ADX analysis of NCA oxalate can be seen that the sample has high nickel content and small cobalt and aluminum content. X-ray diffractogram of as prepared NCA, the peaks observed in this figure will index to CCPTS. The FTIR spectra of NCA slightly observed a peak at wave number around 3,400 can be attributed to the presence of water molecule in the sample. This can be caused due to water entrapment on the surface of the NCA particle due to humidity. The particles have clear edge and slightly smooth surface after a sintering process, and at a high temperature, the particle morphology is sustained from its original form of NCA oxalate, even though CO2 was decomposed during the calcination process, leaving porous particle. However, high temperature sintering may remove the porous particle into dense particles. The electrochemical performance analysis data for the NCA battery charging data has a larger capacity of 210 mAh per grams, and at discharge has capacity of 142 mAh per grams. The cycle performance of NCA LiPF6 graphite cell under the current rate of half C with the operating voltage of 3 until 4.3 volt. Based on the feature, the cell have Coulombic efficiency of about 100%, which indicates good lithium-ion reversibility. However, after 100 cycles, a capacity drop can be observed clearly. At the current rate of quarter C, the specific discharge capacity of the cell is about 110 mAh per grams, which is 91% compared to capacity tested at 0.1 C. At the end of the cycle test, the specific discharge capacity of the cell is about 88 mAh per grams, which is 80.1% compared with the starting capacity. 100 time multiplication of previous lab scale production was conducted. 2 kilograms of NCA product was synthesized and characterized. The production facility can be seen in this figure. The NCA precursor solution were reacted with ammonia and oxalic acid in a continuously stir reactor. The slurry was filtered and was using centrifuge filter, and the cake will dry in vacuum oven. The precursor was milled with lithium hydroxide using ball mill machine. Then the composite was fired in a large muffle furnace under oxygen flow. The characterization of NCA oxalate and NCA product produced at 1 kilogram per batch scale, labeled as NCA-OLS and NCA-LS respectively, can be seen in this figure. The initial specific charge and discharge capacity of NCA-LS are 210 mAh per grams and 136 mAh per grams respectively, which is lower than NCA product produced at lab scale. The cycle performance was conducted at 32 mAh per gram, where the cell exhibit more stable performance owing to low cation disarrangement, which indicate by ratio value. A simple oxalate precipitation technique was successfully applied to produce the NCA cathode material of lithium-ion batteries. Based on the SRT and FTIR analysis, nickel-rich oxalate precursor was successfully formed by the reaction of a solution containing nickel, cobalt, and aluminum ion with oxalic acid. After the heating process, a highly crystalline material with good structural property NCA powder was obtained, which was confirmed by SRT and FTIR analysis. The initial discharge capacity of the obtained NCA was 142 mAh per grams, measured at the charge discharge current of 0.1 C. Scale up production of NCA powder with process capacity of 2 kg per batch is conducted. The results are satisfying. However, there is room for many improvement. We can conclude that the overall process is promising to be further developed in the future. That's one. And this is the end of my presentation. Thank you and good afternoon.